The vapor pressure of a substance is due to the fact that liquid will evaporate to a certain extent. And if you do this process in a closed container, the amount of liquid that has gone into the gas phase will create a partial pressure within the container. This is referred to as the vapor pressure. Shown here is an apparatus that could be used to measure the vapor pressure of a liquid. In essence, we have a filter flask that is then attached to a U-tube that contains mercury. If the level of the mercury in the U-tube is equal before the liquid is added to the flask, and then the liquid evaporates to some extent within the flask, this will create the partial pressure for the liquid and then cause the level of the mercury to be uneven, and the difference in those levels of the mercury represent the pressure of the vapor pressure of the liquid in millimeters of mercury. The temperature has a significant effect on the vapor pressure of a liquid because the temperature is a measure of the average kinetic energy necessary for the molecules to break up through the surface tension of the liquid and get into the gas phase. So if we have a Boltzmann distribution of molecules having certain kinetic energies, some of the molecules will have enough kinetic energy to cause the evaporation process to occur as shown here. But if we were to raise the temperature, the distribution would shift so that there would be a greater proportion of molecules having sufficient kinetic energy. Therefore, the vapor pressure goes up. Shown here is a plot of the temperature as related to the vapor pressure in millimeters of mercury for water, and you can see that the vapor pressures increase significantly as you raise the temperature up to 100 degrees Celsius, which is the so-called normal boiling point for the water. You'll notice that the normal boiling point is defined as the temperature at which the vapor pressure equals the 1 atmosphere, and this then results in the formation of the bubbles within the liquid. If we go to another liquid that has weaker intermolecular forces, the vapor pressures increase at a given temperature, and therefore the normal boiling point goes down because it takes less energy to break the intermolecular forces and create the molecule in the gas phase. Likewise, if we then go from carbon tetrachloride to something like chloroform, where the polarizability of the molecule is significantly decreased, then the intermolecular forces also decrease. It makes it easier to get it into the gas phase, and again the boiling point goes down. And then finally we go to something like diethyl ether, which boils at a fairly low temperature, just slightly above room temperature, and under 1 atmosphere of pressure. So these liquids get increasingly volatile as the intermolecular forces weaken. Turns out that the vapor pressure is created because of the kinetic energy associated with the molecules breaking through the surface and breaking the surface tension along with any intermolecular forces in the liquid phase. So the stronger the intermolecular forces, the lower the vapor pressure. So there's an inverse relationship between these two properties. If we look at some data, we see that glycerol, which has relatively strong intermolecular forces in terms of the hydrogen bonding that is occurring, has a pretty low vapor pressure. Compare that to water, which has slightly fewer hydrogen bonding interactions, per molecule and has a lower molar mass. Therefore, the vapor pressure goes up a little bit. And if we go to look at something like chloroform, which all it has is dipole-dipole forces, now our vapor pressure goes up even more. And then finally we get to something that has nothing but London dispersion forces, and now we have a significantly high vapor pressure for something like pentate. Turns out that the Claus-Clapeyron equation can be used to predict the relative vapor pressures of a particular liquid at two different temperatures, and so this turns out to be a logarithmic relationship between the vapor pressure and the temperature in Kelvin. The equation is shown here, where the natural log of the ratio of two pressures is equal to the change in the enthalpy of vaporization divided by the gas constant times the difference in the inverse of the two different temperatures. So again, the variables P is the pressure under one condition of temperature, and P2 is a second condition of pressure and temperature. And the delta H of vaporization is typically in our units of kilojoules per mole. And of course, the gas constant, it needs to be in terms of joules. So instead of the 0.0821 liters atmosphere mole K that we use in the gas law, we use the 8.3145 joules per Kelvin mole. Again, we want to make sure that we have agreement of units between the enthalpy of vaporization and the gas constant unit of joules. As an example of a question involving the Claus-Clapeyron equation, for example, estimate the vapor pressure of chloroform at 24.8 degrees Celsius. Given that the boiling point of chloroform is 61.7 degrees Celsius and the heat of vaporization is 31.4 kilojoules per mole. We have the Claus-Clapeyron equation, so we want to plug in our variables that we know. In the case of the P1, since we've been given the boiling point under normal conditions, which would be 1 atmosphere, that's equivalent to 760 millimeters of mercury, and we have to make sure that we convert our temperatures into Kelvin by adding 273. The T1 has to be the temperature that is the boiling point, so the 334.85 Kelvin is T1. T2 is the temperature of 24.8 degrees Celsius plus the 273. And of course, we want to make sure that we convert our enthalpy of vaporization into joules to make sure that it agrees with the gas constant units. We then can go ahead and do our math, solving all of the numbers on the right hand side of the equation. Gives us a negative value of 1.3967. That's equal to the natural log of P2 divided by the pressure of 760 millimeters. And so if we then do an anti-log on both sides, using your calculator, can then end up with a situation where you have P2 divided by 760 is equal to the anti-log of negative 1.3967. The anti-log of a natural logarithm is simply taking the base e and raising it to the exponent of negative 1.3967. And at that point, then plugging in your calculator and then rearranging the equation for P2, we come up with a pressure of 188 millimeters of mercury. which is pretty much what you should expect. If you are lowering the temperature, the vapor pressure should go down significantly. By definition, the boiling point, or the normal boiling point of a liquid, is the temperature at which the vapor pressure of the liquid equals the atmospheric pressure exerted on the surface of the liquid. If the temperature is less than the normal boiling point for water, the kinetic energy associated with the motion of molecules may have enough energy to create a cavity or bubble, but the external pressure causes the bubble to collapse, and we don't get the formation of any significant number of bubbles as a result. So, this formation of bubbles only occurs when you get close to the normal boiling point. Once we actually reach the normal boiling point, there will be a significant number of molecules having enough kinetic energy to create the cavities or bubbles within the liquid, and then the atmospheric pressure cannot cause the collapse of the bubble, and the bubble begins to expand. And since the density of the water vapor inside of the bubble is significantly less than the liquid, the bubble would rise to the surface, and then if it was an open container, then the bubble would pop and essentially allow the liquid vapor to, or the vapor to, that was inside of the bubble, to escape. Turns out that the normal boiling point of a liquid is highly dependent upon the intermolecular forces that are involved, and so the lowest boiling substances typically have the weakest intermolecular forces. So, for example, helium has nothing but London dispersion forces and is not very polarizable, so its boiling point is very low, very close to absolute zero. Whereas methane is a slightly larger molecule, a little bit more polarizable, and the boiling point goes up significantly from that of helium. If we go to something like pentane, which has quite a few more carbons and hydrogens than methane, and it is able to create these temporary dipoles due to the distortions of the electron clouds, then the boiling point actually can be above room temperature. If we look at something like methanol, methanol has the ability to have hydrogen bonding. It's still a hydrocarbon, but its boiling point goes up from that of pentane because of the hydrogen bonding. And then finally we have water, which has significant hydrogen bonding interactions and has the highest boiling point of the compounds seen here. The final kind of phase transition that we're going to discuss here is the transition to a supercritical fluid, and this occurs at a critical temperature for any substance where the liquid will actually expand to completely fill the container, and at this point the vapor phase is not completely evident, and so this is a quite unusual substance that has the properties of liquids. It will flow, but the liquid fills the container.